Light, the swiftest traveler in the universe, races across the cosmos at 300,000 kilometers each second. It bends around planets, threads its way through galaxies, and crosses gulfs of interstellar darkness without pause. Yet there exist regions where even light itself comes to an end, where speed, brilliance, and radiance are swallowed whole, leaving nothing behind but silence. At the edge of these regions lies the event horizon, a boundary that functions like a cosmic one-way door. Cross it, and return becomes impossible. Time itself slows to a crawl, stretched thin until moments fracture and dissolve. Matter is pulled apart, stripped of all identity, and folded into the abyss. These are black holes, objects that are not merely things, but questions. They are paradoxes made solid, carved into the fabric of existence by gravity, pushed to its ultimate extreme. When a massive star collapses under its own weight, it does not simply die, it disappears into its own reflection, leaving the universe to wonder what remains hidden inside. To fall toward a black hole is to fall toward silence. To stare into one is to watch the cosmos confront its own vanishing point, and to study them is to push human thought against the very limits of reality itself. This is the story of black holes, gateways, mysteries, and mirrors of the unknown. If you are new here, join the journey. Like, subscribe, and let's begin. In the year 1915, Albert Einstein presented a theory that would change the way humanity understood the universe. His general theory of relativity described gravity not as a force pulling between masses, but as the curvature of space-time itself. Stars and planets did not tug invisibly on one another, as Isaac Newton had believed, but instead bent the cosmic stage on which they moved. And yet, hidden within these equations was a shadow, a prediction so extreme that even Einstein himself doubted its existence. That shadow was revealed only a year later, in the midst of war. While cannons thundered across Europe, a German physicist named Karl Schwarzschild, serving on the front lines, quietly worked through Einstein's new equations. Amid the chaos of trenches and artillery, he derived a solution that seemed less like a product of mathematics than of nightmare. His calculations suggested that if enough matter were compressed into a small enough region, space-time would collapse inward. The escape velocity would exceed the speed of light. Nothing, not matter, not radiation, not even time itself, could ever break free. What Schwarzschild described was not yet called a black hole. In fact, in his own day, the concept was dismissed as a curiosity. Even Einstein himself insisted that such objects could not exist in nature. They were mathematical monsters, abstract phantoms produced by equations stretched too far. Yet, like seeds planted in darkness, the equations would wait for decades before the world was ready to confront their meaning. As the 20th century unfolded, astronomy turned its gaze to the life and death of stars. Scientists began to unravel how stars are born in clouds of hydrogen, how they burn with nuclear fire, and how they die when their fuel runs out. Small stars like the Sun fade gently into white dwarfs, but the fates of larger stars were more violent, more catastrophic. They collapsed under their own gravity, forming neutron stars, objects so dense that a teaspoon would weigh billions of tons. The Indian physicist Subrahmanyan Chandrasekhar calculated in the 1930s that there was a limit to how massive a star could be. Before even neutron degeneracy, the quantum pressure-resisting collapse would fail. Beyond this threshold, now called the Chandrasekhar limit, no known force could hold the star up. Gravity would win completely. The star system, their energy output defied ordinary physics. No normal star, no cluster of stars could explain such fury. Something compact, something voracious, had to be feeding them. Meanwhile, closer to home, X-ray astronomy revealed peculiar binaries, star systems in which an invisible companion siphoned matter from a partner star. One such object, Cygnus X1, became the first widely accepted candidate for a black hole. The evidence was indirect but persuasive. The unseen companion was too massive to be a white dwarf, too heavy to be a neutron star. Its presence was betrayed only by the violent X-rays emitted as stolen matter spiraled into oblivion. The language to describe such enigmas was still unsettled. For decades, scientists spoke of frozen stars, collapsed objects, or gravitational singularities. It was not until the 1960s that the American physicist John Wheeler, himself a poet of scientific language, gave them a name that would endure. He called them black holes. The term captured their essence: regions of darkness from which no light returns, wells of gravity with no bottom. With that phrase, the monsters of mathematics were reborn as astronomical reality. The black hole was no longer just a quirk of Einstein's equations or a contested idea debated in lecture halls. It was a cosmic presence, stitched into the very fabric of the universe. They were no longer only predictions, but actors in the great play of galaxies and stars. And yet, even in their discovery, they carried an unease. For black holes did not merely expand astronomy, they shook the foundations of physics itself. They forced humanity to ask whether the universe harbored places where time ceased to exist, where matter was erased, where the rules of nature fell silent. The birth of the abyss was not a single moment, but a slow dawning, beginning with Schwarzschild's wartime equations, growing through Chandrasekhar's limit, quickening with the discovery of quasars, and finding its name through Wheeler's metaphor. Each step carried the same uneasy recognition. The universe was stranger, darker, and more violent than once believed, and behind every star's light burned the quiet possibility of collapse, the silent invitation into a gravity from which there is no return. This was the beginning. What had once been dismissed as monsters of mathematics were revealed instead as monuments of nature. And the deeper science looked into the abyss, the more it began to realize. The abyss was looking back. For much of the early 20th century, black holes remained imprisoned in mathematics, caged within the abstract corridors of Einstein's equations. To imagine them as real was to imagine a universe that defied all intuition. A universe where matter could be crushed to infinite density, where light itself could be stripped of its freedom, where the very laws of cause and effect dissolved into silence. Even Einstein, whose theory of relativity had birthed the idea, resisted its consequences. He believed nature would not allow such extreme distortions of space-time to exist. His equations may have hinted at collapse, but he trusted the universe to protect itself from such extremes. To him, black holes were aberrations of thought, curiosities born of equations stretched too far, not entities that could dwell in the sky. The central horror lay in the concept of the singularity, the heart of the black hole, where density becomes infinite and volume shrinks to nothing. At a singularity, mathematics falters. The equations of relativity, so successful in describing planets, stars, and galaxies, simply break down. Time and space, normally continuous and predictable, reach a point where they cease to make sense. If such places were real, then physics itself had boundaries it could not cross. For scientists, this was both terrifying and intoxicating. A singularity was not merely a region of great gravity. It was a wound in the fabric of understanding, a reminder that the laws of nature might be incomplete. The 1960s and 70s brought this tension to a crisis. New generations of physicists began to ask whether black holes were not just mathematical shadows, but inevitable outcomes of cosmic evolution. Among them were Roger Penrose and Stephen Hawking. Their work would shock the scientific world, transforming black holes from speculative curiosities into unavoidable certainties. In 1965, Penrose published a groundbreaking paper that changed everything. Using the mathematics of relativity, he proved that once a massive star begins to collapse under its own gravity, the process cannot be stopped. No pressure, no force, no exotic matter can resist it. Collapse, he showed, is inevitable, and it leads to a singularity. His theorem removed the hope that singularities were mere artifacts of perfect symmetry. Instead, they were woven into the very logic of space-time. Under realistic conditions, they must form. The scientific community reeled. Penrose had shown that black holes were not strange exceptions, but natural consequences. They were not unthinkable, they were unavoidable. Stephen Hawking extended these ideas further. In the early 1970s, working with Penrose, he demonstrated that the universe itself may have begun with a singularity. That the Big Bang was not just an expansion of matter, but the eruption of space-time from a point where the known laws of physics collapse. Suddenly, singularities were no longer confined to the hypothetical interiors of collapsed stars. They were part of the cosmic origin story itself. The shock was profound. For centuries, physics had marched toward greater certainty. Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, each step seemed to reveal deeper coherence, a universe bound by elegant rules. But black holes revealed cracks in the edifice. Here were objects that consumed all knowledge, that hid their interiors behind horizons, that broke the continuity of cause and effect. The universe was no longer smooth, predictable, or fully knowable. It contained regions where understanding could not follow. This realization sent ripples far beyond physics. If singularities existed, then the very notion of reality had edges. The causal chain, the sequence of events leading from past to future, could disintegrate. The laws of physics, once thought to be universal, could fail inside the abyss. Black holes were not simply astronomical oddities, they were existential warnings. The transition from unthinkable to inevitable unfolded slowly, but with the weight of inevitability. As observations mounted, quasars burning with impossible luminosity, X-ray binaries, whispering of invisible companions. The mathematical certainty of Penrose and Hawking met the empirical reality of the cosmos. The monsters of theory had revealed their shadows on the sky. To scientists of the mid-20th century, the shock was not merely in finding that black holes might exist, it was in realizing that the universe itself demanded them. Relativity left no room for compromise. Collapse beyond a certain point did not merely suggest a black hole, it required one. For Einstein, who had died in 1955, this was a fate he had never fully accepted. But his equations, like prophecies, had outlived him. They spoke of horizons where time stands still, of singularities where understanding fails. And his successors were forced to confront what he had resisted, that the cosmos does not obey our sense of comfort. By the 1970s, the debate was no longer whether black holes could exist, but how many the universe contained. From impossibility to inevitability, the transformation was complete. The abyss was real, and its presence shook the foundations of science. What followed was a deeper dread. If black holes exist, then so too do their paradoxes. What happens to matter that falls inside? What becomes of information, of memory, of the history of particles once they cross the horizon? These questions, raised by Hawking in the years to come, would ignite the next wave of shock. But already, by the close of the 20th century's second act, the impossible had been made real. The universe had revealed a truth both sublime and terrifying, that among the stars lie regions where physics dies, where the known laws of reality break, and where existence itself is called into question. Black holes had moved from the edges of thought to the center of mystery. Their very presence a reminder that nature holds secrets too deep for certainty, too vast for comfort, and once seen, they could never again be unseen. For decades, black holes remained creatures of theory, dark specters born from mathematics, whispered about in equations, but hidden from sight. Their very nature seemed to forbid observation. How could one see what allowed no light to escape? How could science measure a silence or capture the outline of nothingness itself? And yet, the universe speaks in many voices, not all of them visible. Long before human eyes glimpsed the abyss, instruments began to listen to its echoes. In the middle of the 20th century, a revolution unfolded in astronomy. The night sky, once revealed only through lenses and mirrors, was opened anew through radio waves. Radio telescopes pierced the heavens with unheard ears, detecting signals that no eye could ever see. What they found astonished the world. Far beyond the Milky Way, radio dishes detected beacons brighter than entire galaxies. These objects, soon called quasars, short for quasi-stellar radio sources, shone with unimaginable power. Though they appeared as faint points of light, their luminosity dwarfed that of hundreds of billions of stars combined. And yet, they were confined to volumes no larger than our solar system. What kind of engine could compress such vast energy into such a small region? Nuclear fusion, the fire of stars, was far too weak to explain it. No conventional process of physics could match their fury. Slowly, reluctantly, scientists came to accept a possibility both terrifying and elegant. Quasars were powered by the hunger of black holes. Supermassive black holes, millions or billions of times the mass of the sun, devouring matter at their edges. Gas and dust, spiraling inward, heated to temperatures of millions of degrees, unleashing torrents of energy before crossing the event horizon. Here lay one of the great paradoxes of nature, that the brightest lights in the cosmos arise from the darkest objects. A black hole itself gives off no light, yet the violence of its gravity ignites a blaze so powerful it can be seen across billions of light years. Around the silent heart of darkness, The universe burns with brilliance. Closer to home, other clues emerged. X-ray astronomy, pioneered in the 1960s, revealed strange stellar systems where invisible companions tormented visible stars. These were X-ray binaries, pairs of stars where one, unseen, stole matter from the other. As the captured gas spiraled inward, it released floods of high-energy radiation. In systems like Cygnus X1, the mass of the hidden companion was too great for it to be a white dwarf, or even a neutron star. Only a black hole could explain its gravitational grip. The cosmos, once thought serene, was revealed as predatory. Stars were torn apart, their remnants dragged into orbits of despair, their very substance consumed by companions that could not be seen. But how could science study what lay beyond the horizon itself? The event horizon was a perfect veil. Nothing escaped from within. Only the surrounding chaos, the whirling accretion disks of superheated matter, the jets of plasma launched at near light speed, could betray the presence of what lay hidden inside. The paradox was sharp. The black hole could not be observed directly, and yet its influence was unmistakable. Science could not see the thing itself, but it could trace its shadow in the world around it, like footprints left by an unseen giant. The Hubble Space Telescope, launched in 1990, added further weight to the case. With unmatched clarity, it peered into the hearts of galaxies, revealing stars orbiting invisible centers with extraordinary speeds. In the galaxy M87, Hubble traced motions suggesting a central object billions of times the mass of the Sun. The only explanation was a supermassive black hole. Later, the Chandra X-ray Observatory deepened the view. It revealed high-energy emissions from gas collapsing into these giants, offering clues about their temperatures, dynamics, and violence. Piece by piece, an invisible reality was being sketched through its consequences. And then, in April of 2019, history shifted. For the first time, humanity looked into the abyss and captured its outline. The Event Horizon Telescope, a network of radio observatories linked across the globe, combined its data to create a planet-sized eye. With it, scientists turned their gaze toward M87, a giant elliptical galaxy 55 million light-years away. The image it produced stunned the world. A glowing ring, orange against black, blurred at the edges by distance and gravity. At its center, a hollow shadow, the silhouette of the event horizon itself. Humanity had seen the unseeable. It was not a sharp photograph in the ordinary sense, but a triumph of persistence, a synthesis of signals gathered from every corner of the Earth. The dark heart of M87 had revealed its outline, and with it, proof that the abyss was real. The paradox was finally embodied in light, an image of darkness defined not by what it emitted, but by what it erased. Yet this achievement was more than scientific. It was profoundly philosophical. For the first time, the human species, bound to a fragile planet, had looked across millions of light-years to glimpse the architecture of nothingness. A black hole, once dismissed as mathematical fantasy, once doubted even by Einstein, now stared back, its shadow etched into the canvas of reality. Still, the mystery only deepened. The Event Horizon Telescope had captured a boundary, but not what lay within. The singularity remained hidden, unreachable, forever cloaked. Science had stared into the eye of darkness and seen its edge, but the center, the heart of infinity, remained concealed. How does one measure what cannot be touched? How does one describe the silence that devours time itself? The black hole stands as both a triumph and a reminder that knowledge can reach to the horizon, but no further. That even in the age of telescopes and satellites, the universe keeps some secrets sealed. And yet, it is this very resistance that makes them so compelling. Black holes are not just destinations of matter, they are boundaries of understanding. To study them is to test the strength of physics itself, to push equations to their breaking point, to confront the abyss with tools forged from curiosity and reason. The eye of darkness had been glimpsed, and from that glimpse arose both wonder and dread. For in the outline of a black hole, humanity had not only seen the death of stars and the hunger of gravity, it had seen a mirror, reflecting the limits of knowledge and the fragility of existence itself. Time, the silent rhythm of existence, seems immutable. It governs the rise of stars and the fading of galaxies, the slow unfolding of mountains, the heartbeat of planets, the aging of every living thing. Yet around a black hole, this ancient metronome fractures. At the edge of such an abyss, Einstein's equations reveal a truth so strange that it unsettles the foundations of reality. Gravity, in its relentless pull, does not merely bend space, it bends the very tempo of time. This is gravitational time dilation, the slowing of the clock as mass deepens its grip on the cosmos. For a distant observer, the story of matter approaching a black hole becomes a cruel paradox. A star drifting too near does not seem to fall. Its light grows redder, stretched into longer and weaker waves, until it fades into invisibility. And the star itself, from afar, appears to hover motionless at the edge, frozen forever on the threshold of the event horizon. The fall seems eternal, yet inside, the clock of the doomed matter ticks on. For the traveler carried into that abyss, the plunge is not slow, not frozen, but swift and absolute. The horizon is crossed in moments, and there is no pause, no halt, no mirror of eternity. To them, time flows naturally, each second following the last with its usual rhythm. The contradiction is not illusion, but truth. Two realities at once, bound by the geometry of space-time. Einstein's relativity predicted this fracture in experience. The universe offers no single, absolute clock to govern all things. Instead, each observer, each path through gravity, carries its own tempo of existence. This principle, radical yet precise, has been tested by experiments around Earth itself. Satellites in orbit tick at different rates than clocks on the ground. Atomic clocks flown on jets confirm the distortion. Time itself is not uniform, but pliable, stretched and compressed by motion and by gravity. But around a black hole, the effect deepens into extremity. The curvature of space-time grows so steep that near the event horizon, the dilation approaches infinity. From outside, the clock of the falling traveler slows to near stillness, while within, the descent races forward unstoppably. And then, beyond the horizon, mathematics tells of something stranger still. Inside this boundary, space and time exchange roles. The familiar flow of events dissolves. What was once space, the dimension of movement, of distance, of freedom, becomes time itself, a direction that can only be moved forward into the singularity. And what was once time, the steady arrow that allowed memory, cause, and effect, becomes space, a coordinate without escape. This inversion is not metaphor. It is the structure of relativity itself, written in the geometry of black holes. Once crossed, the traveler cannot turn back, not because of physical walls, but because the future itself points inward, drawing all paths to the singularity. It is not a place one can avoid. It is an instant in time that lies ahead, as inevitable as tomorrow. What then becomes of the idea of free will in such a realm? If space and time are reversed, if the singularity is not a destination, but a moment written into the future, does choice dissolve? Does physics decree that all who fall are bound to meet the end, not by path, but by time itself? Einstein's relativity, triumphant as it is, trembles under this weight. At the singularity, the curvature of space-time becomes infinite. The equations that describe reality collapse into nonsense. The smooth fabric of the cosmos rips apart, and our understanding ends. For scientists, this is both terror and wonder. A black hole is not only an object of immense mass, but a boundary where knowledge itself reaches its limits. It is where time, so fundamental to human existence, proves itself fragile, where our deepest equations, born of human genius, break into silence. The philosophical weight is immense. If time is not absolute, if its rhythm falters in the face of gravity, what then of memory, of history, of future? If an observer far away sees an object frozen for eternity, while the object itself experiences a swift demise, which is reality? The answer, relativity tells us, is both. The universe allows no single vantage, no privileged truth. Reality is woven from perspectives, each true in its own frame, yet incomplete without the others. And so, at the edge of black holes, humanity stares into a paradox. We see time torn apart, not destroyed, but divided into irreconcilable truths. The fall is both endless and instantaneous. The journey is both halted and completed. Space is both a path and a prison, and time itself collapses under the weight of gravity. For physicists, the implications ripple outward. If black holes reveal the collapse of time, do they also reveal the seeds of a new physics? Might quantum gravity, still elusive, restore order where relativity fails? Could time itself emerge from something deeper, something hidden beneath the equations, a truth not yet seen? Until such a theory is born, black holes stand as monuments of mystery. They are reminders that even time, the stage upon which all existence unfolds, is not immune to the sculpting hands of gravity, and that at the heart of the cosmos, beyond the reach of sight, the universe may hold not just darkness, but the undoing of reality itself. Black holes were once imagined as eternal prisons of gravity, cosmic vaults that could never be undone. But in the 1970s, a revelation shattered that certainty. Stephen Hawking, combining the quiet mathematics of quantum fields with the curved geometry of Einstein's space-time, uncovered something extraordinary. Black holes were not immortal. They glowed. They evaporated. This phenomenon, Hawking radiation, arises from the restless fabric of the quantum vacuum. Even in emptiness, the void seethes with fleeting pairs of particles, created and destroyed in instants too brief to see. Near the event horizon, this ephemeral dance is interrupted. One particle falls inward, the other escapes outward, carrying with it a whisper of energy. Over immense spans of time, these whispers accumulate. The black hole, once thought eternal, slowly fades away. Yet with this discovery came a riddle far deeper than any before. If a black hole disappears, what happens to the information it once held? The properties of every atom, the details of every star, the imprints of every particle that ever crossed the horizon. Are they erased from the universe forever? Quantum mechanics insists this cannot be. The laws of physics decree that information is never truly lost. But relativity, married to Hawking's radiation, seems to insist that it is. This is the information paradox, a wound at the heart of modern physics. If information vanishes inside black holes, the foundations of quantum theory collapse. If it survives hidden or transformed, then relativity itself may need rewriting. The paradox stands as the clash of two pillars of science, each undefeated in its own domain, yet contradictory when brought together at the edge of the abyss. The implications are staggering. Some theories suggest the information is encoded in the radiation itself, hidden in subtle correlations between escaping particles. Others envision the horizon as a kind of hologram, a cosmic screen storing the data of everything that enters. This holographic principle, born from black hole physics, has since become a vast field of research, suggesting that the three-dimensional universe itself may be a projection of information inscribed on a distant boundary, a reality woven from memory, not matter. But the debate does not end there. The firewall paradox emerged in the 2010s, challenging even the holographic picture. If information escapes through Hawking radiation, then the horizon itself cannot remain smooth and quiet. Instead, it must burn with unimaginable energy, a wall of fire that incinerates anything that falls in. Such a fate contradicts Einstein's principle of relativity, which promised that a traveler should cross the horizon without violence. The paradox deepens. Is the black hole a furnace of destruction or a gentle curve of space? Science, for all its power, cannot yet decide. At the heart of the debate lies the singularity itself, that point of infinite density where space-time collapses into nothing. Here, the known laws of physics dissolve. Cause and effect unravel. The universe offers no answers, only silence. Some imagine that at the singularity, information is destroyed utterly. Others argue it is preserved in a hidden form, awaiting release through unknown mechanisms. Perhaps the singularity is not a point at all, but a bridge to another universe, a passage through which information slips away, only to re-emerge elsewhere. Each theory is bold, yet none are complete. Quantum physics and general relativity, two unmatched descriptions of reality, cannot yet be reconciled in the furnace of the black hole. The search for quantum gravity, a theory that unites the very small with the very large, is driven by this paradox, by this wound carved into science by the darkness of collapsed stars. The philosophical weight is immense. If information can be lost, then the universe itself forgets. History, identity, the memory of existence would not be eternal but fragile, erasable. If instead information survives in hidden form, then reality may be stranger than imagination allows. A universe of holograms and encodings, where nothing is ever truly gone. In this paradox, black holes stand as both destroyers and preservers, as prisons and as libraries. They challenge humanity to ask what it means to know, to remember, to exist. And beyond their horizons, in the silence of the singularity, the greatest riddle of physics waits, unanswered, until a new theory arises, one that unites the quantum with the cosmic. The paradox remains. The mystery deepens, and black holes continue to guard the secret of information, holding within their darkness the fate of knowledge itself. The paradox of black holes left physics standing on a knife's edge. General relativity painted them as perfect prisons of gravity, ruled by geometry and mass. Quantum mechanics whispered otherwise, insisting that nothing could vanish without trace. Somewhere in the tension between these two truths, the future of physics was waiting to be written. It was into this abyss that new theories ventured, weaving together bold mathematics and daring speculation, searching for a bridge across the deepest rift in science. The first to rise was string theory. Instead of point-like particles, the fundamental ingredients of the universe were envisioned as tiny vibrating strings, each oscillation giving rise to a different particle. In this picture, a black hole is not a featureless singularity, but a collection of countless microstates, hidden beneath the horizon. These microstates encode the information of what falls in, storing it not in destruction, but in intricate order. The singularity, once imagined as a point of infinite density, is replaced by the vibrating patterns of strings, a cosmic choir humming in dimensions beyond sight. Through this lens, the abyss is not empty. It is structured, layered, alive with hidden possibilities. Another path led to loop quantum gravity. Here, space and time themselves are not smooth continua, but woven from discrete quanta, atoms of geometry linked together in a vast network. As matter collapses, space-time cannot shrink indefinitely. Instead, the weave of geometry resists, preventing a true singularity. A black hole in this picture becomes a cosmic bounce, a place where collapsing matter might rebound into a new phase of reality. Loop quantum gravity suggests that black holes may be birthplaces as much as graves, cradles of new universes budding from the ashes of stars. Beyond these competing visions lies the holographic principle, perhaps the most radical of all. Born from studies of black hole entropy, it suggests that the true information of the universe is not stored within its volume, but on its boundaries. Like a hologram, reality may be a projection from a two-dimensional surface inscribed with all that exists. The event horizon itself becomes a cosmic ledger, recording every particle, every photon, every echo of matter that crosses its threshold. In this view, nothing is lost. The universe remembers everything. The abyss is transformed into a mirror, reflecting the truth that information is eternal, even when it seems to vanish. Yet speculation reaches further still. Einstein's own equations hinted at wormholes, Einstein-Rosen bridges, tunnels through space-time connecting distant points, or even separate universes. If black holes harbor such passages, then the singularity may not be an end, but a doorway. Matter that falls into one black hole might emerge from another, across vast gulfs of space, or even in realms beyond this cosmos. These bridges may be unstable, fleeting, torn apart by the violence of collapse, and yet, in the mathematics, they remain possible, a suggestion that black holes may be less like tombs and more like gateways. Some physicists have speculated that every black hole could be a seed of a new cosmos, that inside each horizon lies not destruction, but expansion, a universe unfolding beyond the sight of our own. In this vision, the multiverse blooms from collapse. Every star that dies may give rise to a new creation, a chain of realities born from gravity's deepest wells. The abyss, once feared, becomes a garden of worlds. These theories do not agree, and none yet stand as the final word. String theory stretches across 10 or 11 dimensions, elegant but untested. Loop quantum gravity offers a picture of discrete space-time, yet struggles to match the power of relativity. The holographic principle dazzles with its simplicity, but leaves profound questions unanswered. Wormholes ignite the imagination, yet no observation has revealed their truth. Each path is incomplete, yet together they sketch the outline of a future science, a vision of a universe stranger and more intricate than present knowledge allows. The pursuit of quantum gravity, the unification of the large and the small, remains the greatest unfinished journey of physics, and black holes stand at its center, the crucible where relativity and quantum theory collide, and where the next revolution must emerge. Philosophically, the implications are overwhelming. If the holographic principle is true, then the universe itself is an illusion projected from information at its edge. If wormholes exist, then the walls between universes may be porous, and what we call reality only one of countless domains. If loop quantum gravity holds, then singularities are myths, and death in the cosmos always conceals rebirth. And if string theory is right, then beneath every particle and every black hole lies music, the vibrations of invisible strings singing existence into being. The quantum abyss remains unsolved. But it is here, in the darkness of black holes, that humanity may someday glimpse the ultimate truth of the cosmos. The abyss is not silence. It is possibility, and through it, the deepest paradoxes of reality whisper the promise of answers still to come. For centuries, black holes existed only in equations and imagination, their presence inferred but never seen. They were shadows behind the stars, mysteries whispered in mathematics. To study them seemed almost impossible, for what light could reveal a thing that swallowed light itself? Yet human ingenuity is stubborn. Faced with the abyss, it built tools capable of listening to the tremors of space-time, of mapping the invisible by the echoes it leaves behind. Science, against all odds, learned to hunt the unseeable. The breakthrough came not from vision, but from sound, or something deeper than sound, ripples in the very fabric of space-time. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the faint quiver of space-time as two black holes collided more than 1 billion light-years away. The signal was minuscule, stretching the detectors by less than 1,000th across cosmic time. LIGO, joined by its European partner Virgo and the Japanese observatory Kagra, has transformed black holes from silent enigmas into narrators of their own cosmic histories. But humanity's gaze did not rest there. It reached once more for light, not in the ordinary sense, but through global collaboration. The Event Horizon Telescope, an Earth-sized array of radio observatories, stitched together data from across the world to achieve a vision sharp enough to pierce the edges of the abyss. In 2019, this network revealed the first direct image of a black hole's shadow in the galaxy M87, a glowing ring of plasma encircling the darkness at its core. For the first time, the event horizon was not only theory, but sight. In 2022, the telescope repeated its triumph with the image of Sagittarius A, the supermassive black hole at the heart of the Milky Way. What once lived in mathematics alone now lived in photographs. These instruments continue to grow. Upgrades to the Event Horizon Telescope promise sharper images, even movies of black hole dynamics unfolding in real time. And on the horizon lies LISA, the Laser Interferometer Space Antenna, a mission led by the European Space Agency. 3 spacecraft will orbit the Sun in formation, linked across millions of kilometers, listening for gravitational waves of lower frequencies than LIGO can detect. Where LIGO hears the final seconds of black hole mergers, LISA will hear their long courtships, the slow spirals of supermassive black holes drifting toward collision over millions of years. The cosmos will speak in bass tones too deep for Earth to hear, and science will finally be able to listen. Even the James Webb Space Telescope, though not designed for black holes alone, has joined the search. Its infrared eyes peer through dust, revealing quasars powered by black holes in the early universe. With it, astronomers trace how these objects grew in tandem with galaxies, sculpting the cosmic web across billions of years. Each observation peels back another layer of invisibility, turning darkness into data. But not all experiments happen among the stars. Some unfold in laboratories on Earth, where physicists create analogues of black holes using sound and fluid. In Bose-Einstein condensates, matter cooled to nearly absolute zero, researchers craft sonic horizons where sound waves cannot escape, imitations of the event horizon itself. These sonic black holes radiate faint signals resembling Hawking radiation, giving experimenters a glimpse of what might happen at the edge of real black holes in space. Through these analogues, the abyss becomes not only a distant phenomenon, but something that can be probed with human hands and earthly instruments. And the search does not end here. Next-generation interferometers promise to detect smaller ripples, revealing mergers of black holes across the entire visible universe. Telescopes on the drawing board envision fleets of orbiting mirrors, space-based interferometers sharper than any eye humanity has ever built. Each tool pushes closer to the impossible, to measure what cannot be seen, to understand what defies comprehension. The pursuit is not only technical, but philosophical. To hunt the invisible is to confess that the universe will not reveal itself easily. It demands persistence, imagination, and humility. Black holes are reminders of the limits of perception, yet also of the vast reach of curiosity. By crafting instruments that listen to gravity, that weave together the Earth into one vast eye, that simulate the abyss in laboratories, humanity has extended its senses into domains once thought forever closed. In the end, the tools are not merely machines. They are extensions of the human spirit, reaching toward the edge of knowledge. Every ripple caught by LIGO, every pixel resolved by the Event Horizon Telescope, every faint glimmer traced by Webb is a step closer to seeing the unseeable. Science builds its instruments as bridges of glass, metal, and mathematics, to cross into the dark. And through them, the abyss begins to speak. They sit in silence, scattered across the universe like hidden tombs in a vast and ancient desert. Black holes. Not stars, not planets, not even places in the ordinary sense, but regions where the very fabric of reality folds in on itself. Their presence forces a reckoning, not just with the fate of galaxies, but with the meaning of existence itself. Every black hole begins as an ending. A star that once burned with ferocious light eventually collapses under its own weight. Gravity, the most patient sculptor, takes control. The fusion that once resisted it fades, and the star surrenders to its own mass. In that surrender, a black hole is born. Here lies the first lesson. Even the most radiant lives, the most luminous beacons in the heavens, are not permanent. Their brilliance, like ours, is bound by time. Black holes remind us that mortality is written into the structure of the cosmos. Stars die, galaxies shift and evolve. Even the universe itself marches toward entropy, a gradual cooling, a thinning of energy, a drift into silence. But a black hole is not only a monument to death, it is also a puzzle carved into space-time, a paradox that unsettles the most fundamental ideas of permanence. Physicists once believed that information, the record of matter, energy, and process, could never be destroyed. The equations of quantum mechanics seemed to guarantee it. Yet black holes, with their horizons of no return, appeared to erase information completely. A particle, a planet, or a star falling inside carried with it a library of details: position, momentum, structure. From the outside, all of that vanished. What remained was a black hole described only by mass, spin, and charge. Everything else, the richness of what once existed, seemed gone. This dilemma became known as the information paradox, and it gnawed at the roots of physics itself. If black holes destroy information, then quantum mechanics is broken. If they do not, then there must be a hidden mechanism by which reality preserves memory, even in the most violent collapse. Hawking radiation added another layer to this paradox. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum fluctuations at the edge of their horizons allow them to leak particles, slowly radiating energy. Over inconceivable timescales, this would cause black holes to evaporate. What remains at the end, whether a wisp of information, a fragment of structure, or nothing at all, remains an unsolved mystery. Do black holes threaten the universe itself? If every black hole eventually evaporates, then one by one, the cosmos will lose these anchors of gravity. Galaxies would lose their centers, matter would spread, entropy would increase, and the arrow of time would march relentlessly forward toward a final cold equilibrium. In this vision, black holes are not eternal. They are transient actors, guiding structure for an age, then fading like the stars that birthed them. Yet another possibility lingers in the theories. Perhaps black holes are not simply endings. Perhaps they are portals to something else. Some physicists have speculated that the collapse of matter into a singularity might trigger a bounce, a birth of space-time itself on the far side of an event horizon. In this speculation, every black hole could be the seed of another universe, budding invisibly from our own. We cannot test it. We cannot see past the horizon, but the mathematics leaves the door ajar. If so, then black holes may be more like wombs than graves. In their darkness, creation itself could be taking place. And so humanity, small and fragile, continues to measure these impossible giants. We build instruments that shake with passing gravitational waves. We link telescopes across continents to glimpse the edges of their shadows. We simulate their interiors with supercomputers that run for months, trying to decode how matter and space entwine in their grip. The irony is humbling. Black holes can bend light, distort time, even swallow entire stars. Yet from a small blue world orbiting a mediocre star, a species of fleeting primates has dared to place them under scrutiny. What does this mean for us? It reminds us that we are not the center of the story. Black holes dwarf our existence, but they also reveal our courage, for even light bends to their will. Yet we find ways to follow it, measure it, understand it. Black holes humble us, but they also affirm that we are capable of reaching toward mysteries that once seemed beyond comprehension. There is a philosophical mirror in all of this. To contemplate a black hole is to confront the boundaries of knowledge itself. We do not yet know what truly happens at their core. We do not know if information survives or if it dissolves into a featureless void. We do not know whether they are the end of stories or the beginnings of new ones. And so, each observation becomes more than science. It becomes reflection. When a black hole merges and ripples space-time, we are reminded that even the fabric of reality is not immutable. It trembles like water. When Hawking radiation is described, we are reminded that even the most permanent-seeming darkness is not eternal. It fades, slowly, into the background. When we stare at the shadow of Sagittarius A, we are reminded that every mystery casts a silhouette, but never reveals its face. In the end, black holes may be less about what they are and more about what they ask of us. They ask us to accept impermanence. They ask us to question whether memory itself can survive in a universe that trends towards silence. They ask us to see that endings and beginnings may be entwined, indistinguishable, folded into one another like horizons themselves. And perhaps, in their silence, they offer something profound. Not despair, not finality, but wonder. For as much as they erase, they also create. A canvas for thought, for imagination, for humility. The more we learn, the less certain reality feels. But maybe that is the point. Certainty is a comfort of the small and the temporary. The universe, in its vastness, offers something else. The chance to reflect, to reach, to be transformed by mystery. Black holes are not merely objects. They are not merely the corpses of stars. They are mirrors into the strangeness of existence itself, and in their shadows, we see ourselves, fleeting, fragile, yet searching endlessly for light. Black holes are not merely objects. They are not merely the corpses of stars. They are mirrors into the strangeness of existence itself, and in their shadows, we see ourselves, fleeting, fragile, yet searching endlessly for light. For in the end, the lesson of the black hole is not only about gravity or matter or time. It is about perspective, that endings are never simple endings, that silence may conceal hidden beginnings, that the unknown is not emptiness, but invitation. Perhaps one day when the universe has thinned into silence, when every star has faded and every black hole has whispered away its last breath of radiation, nothing will remain but the memory of the questions we asked. And perhaps those questions themselves are enough to wonder, to measure, to imagine. That is how a fleeting species leaves its mark against eternity. Black holes stand as guardians of mystery at the edge of knowledge. And as long as they endure, so too does humanity's most enduring truth, that even in the deepest darkness, we still reach for understanding. And in that reaching, we find meaning.